All right, so let's go ahead and get started. Thanks everyone for your interest in all things Keck AO. And I'm going to very quickly here turn this over to Peter Wazinowicz, who's in charge of technical development at Keck, and he has a series of slides to go through about a whole bunch of different Keck AO projects. But this is really meant to be a discussion and interaction here. So interrupt at any time, ask questions. If you're not hearing about a topic you want to know about, feel free to jump in. So Peter, you want to take it away with some presentation slides to get us started?
Yep. Muted.
We can hear you.
So, and you can see the presentation, presumably.
Yep, looks good.
So thanks everyone for joining us. We thought we'd go through, I just collected a set of slides to try to go through all the things going on associated with Keck AO right now. And like Jessica said, it would be great to have conversations around these items. But the particular topics that I had in mind were sort of the current and recent AO development, which include KAPA and also a new real-time controller for both Keck 1 and Keck 2. Pyramid wavefront sensor, which is an infrared pyramid wavefront sensor, maybe a little more on Kpic, and some other high contrast work that's going on. Also, Mike Fitzgerald and I, who co-chair the Keck AO Future Study Group, would like to tell you a little bit about that. AO proposal developments, we're working on a number of new things like a higher order deformal mirror, ORCAS, which is an orbiting guide star. There's adaptive secondary mirror as well, and post-on adaptive optics, so idea of observing a couple hours after the sun rises. And then to the extent we have time, we could also talk about future AO instruments, Liger, scales, HISPEC. I also like to get input on what direction people would be interested in terms of a visible science instrument. So I think many of you on the call know what KAPA is, and it's got a lot of elements, all of which are try to picture here. It's a new laser for the Keck 1 telescope, so putting in a Toptica laser like we have on Keck 2 already, and that's already actually being used for science now. It includes a new wavefront sensor camera and a new real-time controller on both telescopes, and we're hoping to get the new real-time controller actually delivered in December to Keck so we can start installing it on Keck 1. And the idea here is that it'll be a much more flexible platform, able to go much higher speeds as well, and where people like our postdoc, Avinash Surendran, can program it. It doesn't require a software engineer at the same level. And then, we combine these pieces to do laser tomography, where the idea is instead of just sampling the cone of light above your telescope with a single laser guide star, you can actually sample the cylinder with multiple laser guide stars in order to sample the atmosphere the science object went through. And to do that, we have to have a way to generate an asterism, so we're breaking the laser light into 4 beacons actually. We actually have to be able to put the 4 beacons on the same wavefront sensor camera. And we actually have a daytime system to simulate that asterism as well, so we can debug the tomography stuff. We also want to take our near-infrared tip-tilt sensor trick and not just use it for a single region of interest in a 100 arcsecond field, but be able to have multiple tip-tilt stars in order to deal with tip-tilt anisoplanetism. And another critical part is we want to be able to provide a PSF, an accurate PSF estimate anywhere in the science field for each observation. And actually, I forgot to include a slide on PSF reconstruction, but Sam Ragland's, I believe, on the call as well, and he's been leading this effort basically currently to validate our PSF reconstruction on science targets. And then all that comes together into the KAPA science, which I have another couple of slides for, which I'll ask Jessica to speak to. And the idea here, well, I'll let Jessica speak to that. And then we also have a lot of student training programs. One is the Astrotech Summer Instrumentation Workshop, which is the goal of that is to attract and retain more women in underrepresented groups and astronomical instrumentation. We also have a pile of postdocs, one technical one at Keck, and 4 or 5 at this point at between UCLA, UC San Diego, UC Berkeley, Caltech, University of Hawaii. And then we also have things like the Keck visiting scholars that can work on KAPA, and also the Akamai science program, or Akamai student program. So again, please ask questions. But I was going to show one more slide related to KAPA, and that is, we know you're not using TRIC, most of you yet, but the Galactic Center group and Dark Matter Energy group have used it a little bit. And this is basically a picture of an OSIRIS integral field image, basically. 900 seconds, I think, in this, using STRAP. And then on the same night, a 900-second image using TRIC. And so TRIC is a near-infrared tip-tilt sensor and can provide much better tip-tilt correction than STRAP is capable of doing. And you can see it in these images here. And TRIC we would have liked to deliver earlier, but we've had the systems being relatively frail, but Jim and his team think they've worked those issues out, and so we're making it available now for science observations. Unless there's questions on KAPA generally, I'll turn it over to Jessica to talk about KAPA science. Jessica?
Hey, yeah. No, I'm here. I'm just waiting to see if anyone had any questions.
You should be checking. I don't know if somebody could check for.
Yeah, I'm checking the Slack and hands and chat and whatnot, so don't worry about that. So the KAPA project has a science component to it. So there are 4 KAPA science surveys, but rather than dive into those, I just thought I'd mention KAPA is here for everyone's science, all of your AO science. But if you're interested in using KAPA and you'd like to learn more about what it's capable of, there's a poster by Blake Drexler, or we have an annual KAPA science team meeting that you may be able to come to once a year, usually a little bit before the Keck science meeting. So here are the 4 key KAPA science surveys, just showing off some simulations that we think we'll be able to achieve. KAPA is really going to open up the sky coverage, so you should be able to look at more areas of the sky with better STREL overall, or better image quality. And with the addition of TRIC, even for the parts that for the objects you can look at today, you should see a big STREL boost going from the current system to the future system with the combination of TRIC plus these new laser tomography AO improvements. So Peter, you want to go to the next slide? And as part of all of the KAPA science surveys, we're building up a suite of tools to make available not to the just to those science teams, but to all science users for KAPA. These include things like an exposure time calculator for OSIRIS, improvements to the OSIRIS spectroscopic data reduction pipeline, which already exists. Those efforts are led by Tuan Do and Shelley Wright at San Diego and Tuan Do at UCLA. There will be a simulator, so if you're interested in writing proposals for KAPA and use with OSIRIS, you might be interested in this simulator. We're adding an imager DRP to do fantastic astrometry and photometry with the OSIRIS imager and push all that data through the data reduction pipeline. Simulated PSFs, again, that goes into the simulator, and PSF reconstruction, lots of testing and validation of that on the sky. So these are a bunch of tools that we'll be developing over the next year or 2 and slowly rolling them out so that all of you can use them. Any questions about KAPA and KAPA science tools in particular?
In terms of if you want to talk to other people, I'm the PI for KAPA. Jessica's the project scientist, and the project science leads include Andrea Gez and Mark Morris and Tuan in terms of the Galactic Center, Shelley Wright and Tucker Jones and Claire Max in terms of the galaxy kinematics and metallicity, Mike Liu and Dimitri Maoué in terms of the exoplanet or the gas giant protoplanets science, and Tommaso Treo and Chris Dosnak in terms of the dark matter, dark energy. We got to get a more talkative group here. Okay, so in terms of the near-infrared pyramid wavefront sensor, this is doing science right now. Jason Wang spoke this morning about some science with with Kpic, but also there's science with the vortex chronograph inside of NERC2, and this is a PDS-70 measurement. And so basically, just in front of NERC2, we have a dichroic that provides some light here to the pyramid wavefront sensor. And along with the pyramid wavefront sensor is the plate for the Kpic fiber injection unit. But basically we have the vortex inside of NERC2, and we use the pyramid wavefront sensor. Here's the sort of strails we get. These are a lot of different observations during the engineering. And so you see you get K-band strails of the order of 55% on bright H-band targets, and then it fades off as you get about 12th magnitude. And so it's already doing a lot of great science here. The infrared pyramid wavefront sensor is part of Kpic. Again, we come through the AO system here, and we go directly to NERC2 with the dichroic here, or we can put a mirror here instead and feed all the light to the IR pyramid wavefront sensor and the fiber injection unit that then goes to a fiber extraction unit and into HISPEC. And as this is what the science Jason was talking about more this morning. There'll be a phase 2 with a lot of the pieces that Jason mentioned that'll be coming in the fall of 2021. I don't know if there's somebody here from the Kpic team if they want to add anything to this.
Peter, Randy does have a question or hand raised.
Go ahead, Randy.
Yeah, actually, it's a question for you, Jessica. And one of the things that we'll probably get out of KAPA is better performance at shorter wavelengths. And I'm wondering what science cases will be able to take advantage of that. You know, maybe better astrometry with higher spatial resolution and other things like that.
Yeah, so the higher STREL does allow us to move to shorter wavelengths to get higher resolution, assuming we're still diffraction limited. And I think we'll be diffraction limited in sort of median seeing conditions always at H band, and now a fair bit of time at J band, which we weren't before. Depends on your guide star brightnesses and whatnot. These are for sort of lower brightness stars. And then for bright stars, you might even be able to push into something occasionally like Y band or Z band. And so the science cases there are going to be some of the things that Shelley was showing off for Liger. So like the intermediate mass black hole astrometry or the stellar mass black hole astrometric microlensing programs would really benefit. And then on the galaxy side, there's certain lines that you can only get to as you move to bluer wavelengths. So they would very much like to move even shortward, but I don't think we're going to go as short as they would like to go yet. So yeah, those are some of the cases we know about. Exoplanets, contrast won't improve as we go shorter, so I don't think that will be super beneficial. But maybe for accreting exoplanets, that might be interesting to get more accretion diagnostic lines at shorter wavelengths.
For the dark matter, sorry to continue, for the dark matter case, one of the techniques that we use, the better the resolution, the farther down the mass function we can go in terms of measuring or detecting clumps of dark matter. And so better resolution is always better for us.
One question we should be asking ourselves at some point is if we want to use OSIRIS or Liger at shorter wavelengths. Right now our cutoff is at 1 micron, right? We send everything short of 1 micron to the wavefront sensor and everything above that to the science instrument. But both of those instruments are capable of working down to 800 nanometers if we can provide the performance. So we could change the dichroic at the expense of, sort of a limiting magnitude for wavefront sensing, potentially. Less of an issue, of course, when we're using near IR sensors for some of the wavefront sensing.
Yeah, so I think that's definitely something to think about. If you have red optical, very red optical cases past 800 nanometers, we'd love to know about them, both for Liger and for just future AO upgrades. Should we make this exchange? And do you have near-infrared guide stars nearby you can use? Are those bright enough? So we'd have to do a little exploring, but I think that's definitely worth thinking about that science case.
The other thing that I think might be true is that the shorter wavelengths will complement JWST as well. So where their short wavelength capability will be pretty lacking.
That's right. One of the things to remember, though, is as you go to shorter wavelengths, the corrected field of the corrected angle, the isoplanatic angle, gets smaller. So the imager, for instance, you'll see a big degradation in the PSF over the field as we move short of 1 micron with the current AO system, even with KAPA. So that's one shortcoming, and maybe at the end of the slides we can talk about future optical AO upgrades that might correct something like that, MCAO or whatnot.
However, over the IFU field, that isoplanatic effect won't really be very significant.
Yeah.
I don't want to stop the conversation, but I'll move on. Sam, you want to speak to the high contrast stuff? I think Becky's on too. I don't know who else is on.
Sure, Peter. Thanks. Yeah, variety of high contrast imaging efforts underway. It is besides Kpic that makes use of the developments from Kpic and RTC upgrade as well. The efforts are funded through different sources. One is Simon Foundation funding, that is Becky is the PI for that. And we also got the NSF funding, that is again Becky, and Mike Bottoms are PIs, and we have co-PIs for the 3 programs at Keck, 1 for Peter and 2 of the programs are myself, the co-PIs. And we also spent some internal funding through Keck research time to address some of the issues here. The main projects are predictive effect control, where we plan to test the technique with the algorithm with the coronagraph later this year. And the spectral nulling, we tested this with the Shackhartman a couple of years ago. And more recently, we started upgrading the approach for Pyramid WFS sensor. And in fact, we had one run a couple of days ago, and we expect to be ready for sky test in a 3 to 6 months time scale. And the next one, we just started working on electric field conjugation. And the fast and furious is one approach that we finished with the lab test a couple of days ago, and we look forward to a sky test in the coming months. And the electric field conjugation is another approach. Yeah, we are collaborating, with the Laurent PO from a Space Telescope Science Institute. Again, we just started, and we think in about 6 months time scale we'll be ready to sky test this. And there are a few techniques we have been trying to co-phase the telescope segment using the using science instrument, primarily NERC2 on Keck 2. That we have some success on that. We are able to successfully measure the residual segment piston errors and be able to apply correction to the telescope. And we are planning some characterization of the residual segment errors to better understand the source of it, and for instance, the effects of elevation dependency, things like that. We hope to address them in the coming months. That's it, Peter.
Yeah, we've recently anchored the error budget tools for KAPA using galactic center and nightly metric data. And what we find is for LGS observations, we have about 130 nanometers of unknown error, and we think much of that is just the residual telescope phasing. So that's the reason for the emphasis on that area. Becky, you're on the phone, on the call. Do you want to say anything more about these topics?
Yeah, just to elaborate a little bit more on the predictive control. So this project was in part inspired by the work going on at Keck AO. A couple of years ago, Olivier Guillon and Jared Nils published a paper on a method for predictive control that they had started to use at Keck AO called empirical orthogonal functions. And so together with Sylvain Cetre and also Charlotte Bond, we've been demonstrating this first during the day on the Keck AO bench, and then we've been testing it at night as well. So in March, we showed that we got some modest improvement in the residual RMS wavefront error as measured by the Pyramid wavefront sensor with predictive control. But the true test is how this behaves with the coronagraph in and on a fainter star. And so we're hoping to do those tests this fall and winter.
Thank you. Any questions for Sam or Becky or comments? We can come back to topics later if people have questions. So Keck AO Future Study Group. You want to talk about this group, Mike?
Sure, I'll say a few words. So this is a group that was charged by the Keck Science Steering Committee about a year and a half ago to start looking at how to prioritize improvements, potential improvements to the adaptive optics systems at Keck. The long-term vision being that these AO systems are kind of old now, and there are improvements that could be made. And so how do we prioritize those, and how do we link those improvements to science cases and science improvements? And so the group was convened. Peter and myself chair it, and the list is here. Several familiar names, hopefully, to those of you. So if you want to contact the group, feel free to reach out. And so over the last fiscal year, we went through an exercise of examining different possibilities for improving the AO system, the science cases that are linked to them, and the potential impacts for doing such upgrades. And we came up with two high priority recommendations. The first is a high order deformable mirror for Keck 2 initially. And the second is taking advantage of time in the early dawn where the seeing is still good. And if you are able to do infrared truth sensing, you can use a laser guide star and still do adaptive optics even around sunrise. And so those two recommendations came out of the group this past year. The higher order deformable mirror proposal is going to go into the NSF MRI program, and the post-on AO is going to be studied towards its operational impacts. So we understand the AO impacts and the science impacts, but we need to do more operational impacts and do some tests, some on-sky tests in the meantime. More recently, the group has successfully argued for its existence, and we're going to be recharged for this next year. And the topics that we're looking at are adaptive secondary mirror, the ORCAS project, which we've heard about, where this is an orbiting laser guide star, essentially. It's down-looking and doesn't have focal anisoplanetism. And then continuing the study of post-on AO. In addition to those things, we're still looking at the other types of improvements that we could make to the AO system, improving efficiency and stability. There's a lot that could be potentially done, and so we're continuing to look at that. But again, we're meeting over the monthly over the course of the year, aiming for helping proposals and doing internal studies and prioritization. If there's any input, feel free to reach out to us. Peter, feel free to add on to that.
Well, that was good. Thank you, Mike. So every basically June, we'll be making at least in June, making recommendations to the SOC about next steps, which then usually requires a proposal to the NSF or someone to get the money. Yeah. Any questions or thoughts on this? I was going to go a little more into some of these items, these particular items here. So I got a slide on each of those. I'll let you, Sam, would you like to talk to this?
Yeah.
Vicky will talk to the science a little too.
Yeah, basically we propose two upgrade here as part of high order DM. The goal is to improve the performance of the AO and improve the sky coverage and science reach of the system. The first one is replacing our existing DM with a higher order DM. That would enable us to reduce, gain in reducing the residual wavefront errors, basically the ones coming from alias fitting and aliasing error. So we hope to achieve at least over 100 nanometer wavefront error reduction. Perhaps probably more in terms of some of the static errors also we may be able to better sense and correct. And the other upgrade is we are currently on Keck 2, we use visible tip-tilt star and truth sensor, the low bandwidth wavefront sensor, and we are proposing to upgrade the system with a near-infrared system. And again, we want to try a new approach that is using a pyramid wavefront sensor based idea. It's not yet tried elsewhere. And we hope to achieve about H magnitude limit of about 15 on Keck 2. So that would open up many LGS capabilities on Keck 2. And what is shown on the right-hand side is the strand ratio. It's with a higher order DM, we expect to have gain in strand. And on the left is it's a contrast curve. I'll let Becky talk about it. Okay.
Sure. So this contrast curve comes from a simulation that Dimitri Mawe and I worked on using the Python package HCIPy from EmulePore. And what we found is that by switching from the current DM to the new DM, we get a couple of magnitudes improvement in the contrast. And so that would allow us to probe a lower mass regime of planets that may have formed via disk instability rather than like brown dwarfs. It also improves the control radius, so it brings some currently known planets inside the control radius for the first time in the H-band. Another exciting aspect for the exoplanet science is that by enabling some kind of improvement in the visible wavelengths, this might allow Kpic to feed KPF in the future, and this would allow us to do high angular resolution, high contrast characterization of exoplanets. And it would also just improve the observing efficiency of Kpic as well. So those are some of the exoplanet science cases we're interested in.
Thanks, Becky and Sam. So for this proposal, it will be an MRI proposal we'll submit in January. Sam will be the PI and Becky's going to be the project scientist. A nice team there.
Peter, it's worth pointing out for the high order DM, that's specifically for Keck 2, and the infrared capability, the infrared tilt sensing would be available for laser guide star and for natural guide star. So I think that would give increased STREL and better sky coverage for both natural guide star and laser guide star modes on Keck 2 to sort of complement the Keck 1 improvements with KAPA.
Yeah, thank you, Jessica. And the reason we can get away with a higher order DM as we go to laser guide star is because our laser return is so high. So splitting it into 2x2 subapertures for one before or something like that is not a problem. Any questions on that or thoughts? Okay, so ORCAS is an exciting project. In fact, our Nobel Prize winner, John Mather, do you want to talk about ORCAS?
Yeah, I'm very happy to mention what we've been thinking about. We realized a while back that if we could shine a laser down from space, we could make it as bright as you like. And then when you got it, you could do your adaptive optics with it and then get rid of it because it's a narrowband source. So it would have many of the advantages of a natural guide star or for single conjugate adaptive optics, but you could put it where you wanted it. And so the hope would be if you could also upgrade the AO system to go with it, then it would open up new territories of astronomy. So what we are showing on the left chart here is the improvement of angular resolution, which is kind of obvious if you can get a big telescope like Keck to have a diffraction limited performance, then that's wonderfully better than anything that we are currently planning to launch into space, even including the Webb telescope, which is my favorite project. So the possibility is for a small satellite, and the budget for those as defined by NASA is $35 million. So we think we might be able to fit that criterion, which would include both a space piece, an orbiting guide star, and some upgrades to the AO system. So if you could do this, then you could get a lot better performance at a lot shorter wavelength, and that's the hope. So we are interested in people who have identified some key science that would only be possible with this, because that's the thing that makes it possible for us to make a successful proposal. So that's what we're thinking. So next fall, a year from now, we have to send in a proposal if we're going to do this.
And you had a very stimulating virtual science meeting just a few weeks ago.
Yes, we did. We had 85 people came and a lot of very exciting discussion. I would say that active galactic nuclei and black hole studies certainly topped the list of popularity. There's also obviously that NASA does solar system missions, and having the ability to support solar system encounters would be cool as far as NASA is concerned, we hope. So a pretty wide range of science topics are enabled by better visible band performance.
This plot on the right is basically showing you what Strel ratio you could expect with ORCAS, the top light blue curve, because you basically have this very bright source wherever you want it. And so that's where we're heading. And this is another reason we're talking about visible science instruments, because, you know, we're getting Strels in the visible here like we're getting in the infrared now.
Peter, is that Strel with a high order DM or the current DM?
It's with a high order DM. So it's actually a stack up here of, you know, the current performance, then the RTC upgrade, then the high order DM, then some optimization will be able to do.
There, yeah, thanks.
And, you know, there's also been a question about, well, what happens when you go off axis? This is on axis. You come down to this purple curve when you go 10 arc seconds off axis. So the idea is ORCAS could be within 10 arc seconds of your science target, or maybe up to a couple hours.
We also have a question from Sanchit.
Yeah, on this concept, is this like a low Earth orbiting, or where is this orbit, and what is the configurable part of it? What are we configuring about it?
I don't know if Elliot is on the phone. If he is, I'll let him speak to that. Otherwise, I'd say it's a very eccentric orbit. And so it's when it's at the, you know, ends of those orbits where it's, you know, essentially a point source to us. Anything to that, John?
Yeah, it's got to be pretty far from Earth so that it slows down enough to match the orbit, the motion of the observatory, which is around 400 meters a second, which is a lot smaller than low Earth orbit velocities. So 180,000 kilometers out or more. So we're even currently, we're looking even at L2 orbits. We can still make a bright enough star if you need it.
This source, actually, the way the current design has two wavelengths, 1032 and 1064 and 532. So we could actually close the loop either with our Shack Hartman or with our near infrared pyramid, or a combination.
So assuming we wish to do this, then the interesting question is how far can you push it? And what is the new science that opens up if you can even do better in, AO systems than what Peter is plotting here? So, but that's long term.
Okay. Thank you.
One other thing that's worth mentioning is that with ORCAS, you have potentially a source that is of known brightness all the time. So we AO people are not so used to being able to do high precision photometry, but if you had a calibration source in your field, this might open up the possibility of doing very accurate photometry with AO. So tell all your Stellar Pops friends that they might be able to do their photometry now from adaptive optics systems with a calibrator.
Yeah. And my cosmology colleagues tell me they need a few tenths of a % accuracy to reduce the error bars on their cosmological acceleration measurements.
So that would not be with the laser source, that would be with a separate source.
Probably so, yeah.
And I'm also intrigued by the possibility if we can attenuate it enough using one of the laser wavelengths to be a PSF reference in the right, PSF reference in the field.
Yep.
Lots of interesting ideas, and this is sort of a fresh, concept that so people's ideas are very welcome.
Yeah.
Yeah. It makes me curious. Like, how do you keep a laser that's stable with that much power for? I don't know what's the planned lifetime for this mission, or like how long you'd expect this to.
Nominally 3 years. Nothing limits it. Actually, you can keep it going. But we do have to use fuel to get from one target star to another because we have to change the orbit.
Okay.
So, but it's not likely to wear out. And if you wanted to make precise calibration, you would, of course, have to make a multi-method proof that it was as good as you said.
Mm-hmm.
Well, thanks for that, John. I'm going to perhaps move on, cover some other items, but, again, people can, you know where to get more information and you know some people to contact. Adaptive secondary, Phil, you're leading this effort. You want to talk about it?
Sure. Just mention that it's an ongoing concept study right now where we're focusing on the technology of how you deploy an adaptive secondary mirror. In particular, there's this high efficiency technology that TNO has developed that is being demonstrated on the UH 2.2 meter. And we would like to see how that scales in terms of cost and reliability in terms for an ASM on Keck. So the meat of the proposal is to look at that, but we'd like to think about how that then integrates into the Keck AO strategic plan. So we've been talking with AO Future Studies Group and welcome input about how this might correspond to science you would like to do. I guess I should back up and say what motivates an ASM. And there's sort of two broad categories. One is wide field correction of the ground layer of turbulence. And that's something that Jessica, Lou, and Mark Chun have looked at previously in terms of Keck applications. And then there's a second area, which is higher throughput, lower background adaptive optics. And that's particularly interesting at longer wavelengths, starting somewhere in K-band and longer, where you get rid of the telescope emissivity by having fewer warm optics in your beam. So yeah, that's all I wanted to say.
Ideally, we'd have the whatever ASM we had in the telescope, we'd want to be able to use for ground layer. We want to be able to use for higher order fraction limited AO, and we want to use for normal SIG limit as well. So it's got to be a fairly well controlled secondary. It also requires, of course, if we're going to use it for GLAO, it also requires thinking about how we're going to make use of existing instruments or future instruments, how we include wavefront sensing with those instruments, those sorts of questions, and also how we provide the laser guide stars for the GLAO correction. We got the lasers, we just have to provide the guide stars.
Also, we're unlikely to be able to afford 2 of these, so we're talking about one telescope or the other, so opinions on which telescope are also welcome.
Okay, thank you, Phil. So this is one other concept, and I put these 2 plots on to explain why we're interested in this. So the idea would be to be able to continue AO science observations for up to a couple hours after sunrise. And you can see in this plot here, this is median seeing versus local time from measurements on Haleakala. But you can see for the first couple hours after sunrise, conditions are still pretty calm. Temperatures haven't changed a lot yet, and the seeing is still good. So you still have good seeing conditions. The next part is, what's the sky background? So at K-band, these again measurements at Haleakala, but these are sky backgrounds at various pointings away from the sun, and you get something like 3.5 magnitude stainer because we have small images with AO. So the sky is actually reasonably faint, especially at the longer wavelength, so L and M band. And the capabilities we have with AO that allow us to do this is we have a very bright laser return, and all we have to do is notch out the sky background, and we can do that with narrowband filters. And we've actually been exploring, well, why don't you speak to the narrowband filters, Sam? You implemented it.
Yeah, we implemented a narrowband filter on both Keck 1 and Keck 2 in the wavefront sensor for optics. It's 1 nanometer full width of maxima. And we did some tests, 12-light test. We were able to, just verify that the central wavelength is optimal and things like that. And we are kind of ready to try with a laser. Again, with the laser in the twilight, we already did some tests, but we want to really get into the day sky. And we had projected some request. We have request for engineering time in 21A, semester 21A. So we are likely to do some tests with the laser in the daytime in support of this project.
Thanks, Sam. We also have a narrower filter that Mark Chun provided that we hope to test out as well. And then the future study group actually thought about the science. I don't know if Catherine's on the call, but she thought about solar system science and thought there was a lot of exciting stuff there to do, especially in concert with missions around Jupiter or other systems, so that you could be simultaneously doing the space and ground-based stuff or mission prep stuff. And Jessica, you thought about some of the science as well.
Yeah, parallax measurements. Parallax signals are usually maximized at sort of dawn and dusk. So that's one thing to think about. Just getting that pesky AO acquisition that we all have to wait for at the beginning of the night, shift that to before sunrise would be amazing. Other things, comets and what solar system bodies that are sort of at those oppositions or something where you have to observe at dawn and dusk are very useful. And yeah, all of us more hours in the night by pushing engineering things and calibration things that we need to make the AO system better, pushing those into daylight hours would be, or dusk and dawn hours would be great.
It doesn't even have to be an AO night. We could just switch to AO and after 12-degree twilight or something like that. So you could be adding a significant amount of observing time. Other telescopes do this already. IRTF does a lot of daytime observing, for example, and we're trying to learn from their experience.
Yeah, and there are limitations. You do have to have a fairly bright infrared guide star, so it's not the same same observational limits as we get during the night. So just keep that in mind. But it is definitely of extra value, more hours.
And that's the other part of our toolbox, is that we do have infrared wavefront sensors on both telescopes now. Any thoughts on this?
I had a question. So would this, would we first have to start observing post-dawn before we think about AO on top of that, or would that just be something we can do once we start observing? And is that something we're looking at right now?
I'm not sure if I'm getting the gist of your question, but I mean, it's AO that allows us to observe post-dawn, basically.
Oh, okay.
It's only AO. Yeah.
Yeah.
Okay, yeah. That helps, thank you.
Is there another question or comment? You've already heard a lot about other instruments, but maybe the same group hasn't heard it. So Tucker, if you're on the call, can you speak to Liger?
Yeah, yeah, sure. I can say a little bit. So yeah, there was the talk by Shelley earlier today. But yeah, to give the summary here. So Liger is an instrument that we're proposing for Keck that is a imager and integral field spectrograph. And the idea is that it would both be a significant improvement on the capabilities we currently have with OSIRIS, and to take advantage of the new capabilities coming up from KAPA and for any future AO upgrades like we're talking about here. So kind of on the right is a very short summary overview of the layout and the modes. So the wavelength coverage of Liger as spec is down to 0.84 micron. It could be pushed down to maybe down to as far as 0.8, where the detector becomes insensitive. But so this allows you to push below 1 micron if, as Peter, as you said earlier, if you take out the current dichroic and let the light into the instrument. So you can get this with both the integral field spectrograph and the imager. Currently with OSIRIS in particular, the IFS is not really good at the short wavelengths. And so this instrument is designed to be efficient and effective at those shorter wavelengths. Additionally, it goes up to a higher spectral resolution. So there's our 4000 resolution mode, which is similar to OSIRIS currently, and an R of 8000 mode at several different spaxel scales from 15 milliarc seconds to 150. And then an imager to go with that, which is fairly standard, similar to current OSIRIS imager. One of the, well, there are several new capabilities. One of the others that isn't strictly highlighted here is that the sensitivity, especially in the coarser scales, so the slicer integral field spectrograph, is very high. It would give you much better sensitivity on coarse scales than we're getting with OSIRIS right now, which I believe Shelley highlighted as well. So then we have this table kind of going down the purely new capabilities. In addition to just the higher sensitivity that makes everything better, we have the higher resolution mode, the shorter wavelength coverage, a field of view that's 4 times bigger than any other current IFS and even larger than that compared to JWST, and a parfocal parallel imaging that opens up a lot of example science cases and improves all the science that we're currently doing. So I think one key thing to highlight here maybe is that this instrument really is spec to go down into that red optical. And so with some of the improvements coming on, you can take advantage of that. And then with future improvements, this would be an instrument that could get you down to, of order 0.8 microns to do that kind of red optical science.
Thank you, Tucker. Any thoughts or questions on Liger?
Tucker, I had a question. Does the R of 4000 narrow mode also offer sensitivity gains over OSIRIS, or not so much?
So in the lenslets, so the narrow field mode, I don't believe it's a large advantage in sensitivity. It does have a very large advantage in field of view. But I think in raw, if you have, a point source of some magnitude, I don't think it's a huge gain. I think certainly the major gains are field of view and the coarse scale sensitivity.
Okay, thanks.
Jessica, can you remind me how much time we have?
We have another half hour, but it'd be good to not use up that whole time, give people a chance to take about a 15-minute break. So let's keep it to maybe another 10, 15 minutes at most.
Thank you. So I don't know that there's anybody from the scales team on here. There were discussions about scales and HISPEC yesterday. Does anybody have any questions or thoughts on this? Questions will have to be top level since I'm not an expert on scales. But you get a feel here for the contrast and spectral resolution improvements. Of course, it's mostly a KLM, or is a KLM instrument.
I could say a few words about it, Peter.
Thanks, Phil.
Yeah, as Peter mentioned, this is a 2 to 5 micron integral field spectrograph, where one of the key science drivers for it is to explore direct imaging and characterization of exoplanets. And if you think about it, the longer wavelengths are favorable for detecting these exoplanets. So although it doesn't have the same contrast as GPI, working at longer wavelengths is useful, as demonstrated by NERC2 observing a fair number of the direct imaging candidates out there. And then the ability to characterize these planets allows you to get at composition, temperature, things like that. So it has a low resolution mode, and then a separate medium resolution mode with slicer optics that you can switch between in the system.
And this is another case where Keck 1 versus Keck 2 conversations will come up in reasonably short order. So again, your feedback is useful.
Nominally, I think Mark Cass has been planning to put it on Keck 1, but the interaction of the high order DM made private Keck 2.
Yep.
Okay, HISPEC. Dimitri spoke about HISPEC yesterday at a breakout. I don't know if there's anybody from the HISPEC team. I'm scanning down.
I'm co-PI of the instrument, so I can speak a little bit to it.
Sorry, Mike. Go ahead.
Yeah, so HISPEC is fiber-fed high-resolution spectrometers. 2 dewars. One dewar is the blue channel, does Y and J bands. The other dewar is the red channel, does H and K bands. All simultaneously, average spectral resolution of about 100,000 over each band, sampling greater than 3 pixels over most of each band. The goals are to be able to do direct spectroscopy of exoplanets, transit spectroscopy, and precision radial velocity, along with other science cases, sort of covering the bases on exoplanet detection and characterization. It is fiber-fed single-mode fibers primarily. This is done with an upgrade to the Kpic front-end instrument that is currently on K2 AO. And so this is really poised to take advantage of a lot of the AO improvements that we're looking for on K2. But in the interest of time, I'll leave it there, and happy to take questions now or offline discussion.
There's also a laser frequency comb that would be used with HISPEC and in the nearer term with NERSPEC, and we're hoping to potentially implement that in the coming year.
Yeah, funding contingent.
Yes.
Chaz mentioned that in the breakout yesterday.
Right.
Mike, can you use HISPEC with LGS off-axis with your far away tip tilt
Yes, so HISPEC will be able to take advantage of LGS operation. So as long as you can get your source onto the fiber, then it works. The limit will be the acquisition onto the fiber and the ability to track the position of some source on the fiber. Acquisition camera is in the infrared, and some of the potential upgrades to the sort of Kpic acquisition camera are getting a cooled camera or more sensitive cameras to be able to improve that sensitivity. So for faint objects with laser guide star feeds, you're going to be limited by that tracking. So if your object is very red, for example, or you have some sort of red source within the field, of that acquisition camera, then you should be okay.
Thanks.
So far, we've only used the Pyramid wavefront sensor for essentially on-axis targets, but we're upgrading that right now to be able to. We've got field steering capability in there, and we're implementing that now. So you could actually use off-axis targets on the Pyramid and still feed, still feeds NERC2 at least. Yeah, FIU will be a little harder. Okay, thank you, Mike. And I wanted to finish with this slide again, being driven by, the performance improvements from KAPA or the high order DM or ORCAS. I think it's time for us to start thinking about visible science. And, we've thought of some options we already mentioned, potentially using, OSIRIS or Liger to 0.8 microns, upgrading, well, we've thought of upgrading our acquisition camera for parallel, visible, and IR observations, or integrating a test camera with that camera, potentially in the near term, refurbishing some previous Caltech instruments, an IFU or a camera. But we're looking for ideas of what people need and what they'd be interested in, or if they have other ideas for instruments. Who's a visible instrument builder on this call? Unfortunately, there's not many in AO land at this point.
There was the old instrument on Palomar, and I'm blanking on its name.
You're talking about Swift or TMAS?
Swift. I'm thinking of Swift. Yeah.
And that's actually what I meant by this.
Oh, that's right. Of course.
So, have you used Swift?
I have not. I thought about it at one point, years ago, and it looked like it just wasn't going to be terribly sensitive for the kind of extragalactic science I would want to do with it.
Mm.
But, that was with the Palomar, what was it, P1640 system, and, with the souped up Keck system, it could be quite powerful.
Yeah, okay. If we start thinking about Swift seriously, I'd like to get your input on whether it's going to be sensitive enough to do your science. Other people have thoughts?
Yeah, or even more generally, what do you want your AO system to do that it doesn't already do today?
Add something to the Swiss Army knife.
Excellent. Everyone's happy with the plan. That's great.
That's true, but I mean, there's room here for general discussion. You got Jim and Randy here also, from at least Jim now, from AO operations, as opposed to the AO development that's been taking the floor here. If you got questions, here's an opportunity.
Has anyone else been trying interesting things with the AO system, new modes, pushing it in different ways? Tried something and it failed, tried something, it was great. Now's the time to share. Let's see, Carlos, you had a question or a comment?
Yes, I actually have a question. It's about the post-down AO capability, which I mean, in theory, looks really nice. It would be like almost adding 50% of observing time every night, 2 hours before and after, before sunset, sunset and 2 hours after sunrise. But can anybody comment a little bit on how this would be implemented practically from the point of view of the operations, all the different ramifications, the impact that has on how the observatory works right now, the dynamics of day crew night crew, all these kind of things. Is there really a way to implement this from the practical
Carlos,
point
I
of view?
don't think we could do anything before sunset because the seeing is not going to be good before the sun goes down. The seeing stays good after the sunrise because just the air hasn't and the ground hasn't warmed up to have local turbulence.
Right, we weren't thinking pre-sun set. But still, you have the operational issues for the morning and 2 hours extra of support. And we were counting on you, Carlos.
Maybe that's why I'm asking.
I think we just we'd have to staff for that. We'd have to. I mean, we do have an advantage if UNO, which is unintended nighttime operations, in place because people wouldn't have to be at the summit. So that's at least less stress.
Yeah,
but we want to learn from how they do it at IRTF, in terms of staffing, for example. I think all of the issues about, space command, laser traffic control, all those sorts of issues, I think they have solutions to. I think the main issue is actually how we staff it as an observatory. And not put, we may have to trade off against other things, right, within a limited budget. But the value of, 2 hours more is pretty significant. And that could be on both telescopes, of course.
Yeah, Peter, I would add that we thought about the safety aspects and had some discussion with the UNO folks. So probably we'll add some additional sensors and things like that. But yes, on the human resource point, it's too early to think about it or plan about it. Okay.
Yeah, I think there are significant issues with the impacts on the day crews. If the laser's running in the dome, then nobody has access, right?
Yeah, well, I mean, in terms of safety of making sure, sunlight doesn't get in the dome, I'm sure there's ways, I mean, as Sam pointed out, we can deal with that. In terms of the day crew, and the other issue is, calibration of instruments, right? So it would be, day crew doesn't start work late or the regular shift till 9. So going 2 hours extra, especially in the summer, wouldn't be an issue. Although an early crew can be there at 7 in the morning. But, a lot of people use that period of time to do calibrations. And Jim's actually been thinking of doing more effective calibrations that can be used broader. Maybe you want to speak to that, Jim.
Well, we're trying to find ways to ensure that we have the proper balance of summit daytime, early daytime tasks versus the science needs. And all of the additional calibration efforts, they fall in, they're going to fall into the same process of trying to improve the viability of the Keck archive, because what is the minimum set of calibrations that makes science data usable to not only the proposing PI, but also archive PIs.
So we would have to do a lot more careful scheduling of any calibration versus observing late, after dawn with LGS versus the day crew. So there really are scheduling issues to be dealt with, in addition to, more labor potentially. I do see it. Go ahead, Jim or Jessica. I was just noting a question.
Yeah, go ahead, Jim.
No, I said I see Phil's hand is up.
Oh,
Good.
ahead, Phil.
All right. Yeah, let's go, Phil.
Yeah. So, I wanted to ask a question which was sort of answered by Randy when I was writing a proposal, but I wanted to ask it more generally, which is I was trying to help someone write a proposal for LGS where there was really no good guide star available. And the Keck documentation is pretty good on saying, well, here's the level we can go to. But I was just curious whether the, operational experts on the call have any advice of, like, if you really have no good guide star, is there a mode where you can essentially run it with LGS correction only with, some suitably fainter star for low bandwidth wavefront sensor? I'm just curious what your knowledge is on this.
So there's a couple different ways we've done an observation of Mars before, where we effectively did LGS without tip tilt, and it was okay. Other things that we've done in the we don't,
meaning like 0.1 arcsecond images or something like that?
Yeah, it was better than seeing, but not quite to the level that it needed to be to be full on AO. It was looking for it was a methane on Mars study.
But we haven't tried that again since the telescope control system upgrade.
I'm not sure if we have or not. I can't. I'm not sure we have. On very, very faint stars, we've done something before. If you fix the pupil, we've done things where we essentially go to a bright star and sharpen up the correction from the default correction using a bright star with the low bandwidth wavefront sensor, and then freezing the low bandwidth correction, going to a very faint object that's just enough photons to keep the tip tilt sensor on it, and you can get 10 to 15 minutes of pretty reasonable correction. That's a very involved mode, and honestly, we haven't done it really in the last probably 10 years. It takes a lot of coordination, because it would be one of the Keck staff, one of the staff astronomers driving the AO system instead of the observing assistants, because it's a couple steps up in complexity for setting it up to do that. It's how we observed the satellite of Eris.
It'd be worth trying again, because the low bandwidth wave. I mean, then we were projecting off axis, I think.
Correct.
The low bandwidth wave had more work to do. It's got less work to do now, and also if we can get focus from Kpic, instead, again, the low bandwidth will have less to do. So these modes, I think, are things we should be investigating in our ample spare time, Phil.
Well, you get people who say, "Oh, I perfect object, just nothing good as a tip tilt," and it's interesting to try.
There is a question from Jerry Yuan, and Becky, you might want to respond to this too, but I think I have a quick question about predictive wavefront control on Keck 2. After on-sky test, is a plan for this to be available as an option when observing with, for example, NERC 2?
Yeah, so I can say that we would love for that to be the case eventually, but the facilitization is not currently funded.
Okay, thanks.
I don't know that it would be terribly hard to implement, because once we've got the algorithm in the real-time control system, it may be that it's relatively straightforward, but we first want to demonstrate that it's a worthwhile use of the CPU time.
I think at the minimum, we are likely to have the system running all the time. So that will be a first step, then we'll find the funding, or as you mentioned, we'll be able to somehow install it, implement it. So we are getting some disks, from Becky, and we're getting some funding to make sure we're able to save the data, things like that. So that I see it as a first step towards facilitating the predictive control.
All right, it's 2:15 now, so I just wanted to give everybody sort of a 10-minute warning before we reconvene and give us a break. We'll leave the Zoom session open. Everybody's welcome to stay and keep conversing if you'd like, but again, now's a good time to take a break if you haven't, before we hop back over to the regular Zoom at 2:25. So thanks so much, everybody. Yeah, for Peter, for all the slides and everyone else who spoke to them. We really appreciate it.
Thanks, folks. Thanks, Jessica.
Thank you.
Yep.
I'm still here if anybody has additional thoughts. But most people are disappearing. Keith, you haven't said anything. You usually have something on your mind.
Oh, I'm just listening.
Fly on a wall.
I'm waiting for NERC 2 to disappear.
Well,
Are you going to build us a replacement? Yeah.
Well, it's not going to last forever.
It's amazing.
We've grouted it down to the floor, Keith. It's not moving. So
I know I put all the bolts in, but it's interesting to see where it fails.
Although there is talk about replacing, believe it or not, the the control for it.
Oh yes, and that proposal never went in. Yeah, which is a shame. What is predictive AO? Is it like a feed forward?
Yeah, it's using past history basically to predict what the next.
Yeah, okay. In a servo loop, it would be a feed forward kind of thing.
Right. And there's quite a few algorithms out there, but I don't know that any of them are in operations yet. But we're exploring some of those.
You know, as far as daylight or morning observations, 25 years ago, I guess, I did observations of GL229b, where I started out when you lost the guide star, and I took images at K, and then I worked out to L as the sun got brighter, and I was away from the sun. But I must have worked for 2 hours, telling the day crew, I'll be off the telescope in a little while.
That at Keith or at Palomar?
That was a Keck. At Palomar, I've worked all the way through, pretty much until 11 in the morning and started at 1.
Non-AO, speckle or something?
No, just imaging. It's 3 microns. Looking for brown dwarfs and various other things that you can do in the, for 3 microns out, you can work all day, basically. I mean, we used to do millimeter too, but we didn't do that.
Well, I mean, that's the great thing, right? I mean, we've got NERC 2, which can work at KLM band, right? And we could just be using it with AO correction right now, for a couple hours more at least.
Yeah. I mean, you can do it without tip tilts, but the trouble is that, if you had a very fast camera, but the trouble is that that's not the efficient way to do it. You can shift and add at the end, but you need enough signal to noise.
I wonder if we're going to get more interest in this, especially sort of the 3 to 5 microns or beyond with JWST launching, because there's getting more people working at those wavelengths than have been previously. And even small amounts of imaging with even coarse resolution over bigger fields of view, or maybe high resolution spectroscopic follow-up of JW targets at those wavelengths. Those are all things that are possible.
You need much brighter things than JWST can look at usually, because they can go very, very faint. The sensitivity is incredibly good.
Yeah, that's true, but I think there'll be a fair share of brighter targets that they're using for spatial resolution, that web spatial resolution.
Yeah, we'll have a bit better spatial resolution.
Yeah.
But
hey, Jim, on the pre-dawn side, even 15 minutes, I mean, just anything to slide that AO acquisition a little earlier is still totally worthwhile. So even if the seeing is junk, yeah, if we can get the checkout done, then that would be really, really helpful.
Another thing we've been talking, or I've had a conversation with you, Jim, about is not doing the pre-observing checkout.
Yeah.
I mean, how close do you think you are to that?
With the pyramid, excuse me.
We already do a shortened version. We have to close the loops in NGS just to focus the telescope more than anything else. We're the center launch, because of the optical launch telescope's a very fast system, and and we don't seem to do a very good job of predicting a focus all the time. So the laser is often out of focus, and so we need to check that. So you gotta get the telescope in focus first, so then you can use the telescope, the knowledge that the telescope's in focus to focus the laser.
Let me ask a question about the pyramid wavefront sensor. It works in the infrared now.
Right.
And so it could, and I assume if there's a bright enough star on it, it also acts as the tip-tilt star.
Yeah, I mean, it could, and we
I'm thinking of things like IRS-7 around the galactic center, where it not only is close to the center, it's a good bright tip-tilt star.
I think the galactic center is one of those targets that would have extreme benefit from post-dawn observing, right?
Yeah.
And there's no, and with IRS-7, we could, we don't need the laser.
That's what I'm saying. It's a very bright tip-tilt and adaptive star, so you could operate early, but it's a lot of advantages.
Yeah.
Randy and Anna did a test recently using the pyramid on IRS-7. It wasn't a well-formulated test because they were intending to do LGS with NIRSPOW, and Subaru shut them down. Which is also one of the concerns I have about ORCAS, with the beam when it comes down intercepting Subarus.
Yeah, I was wondering about that too.
And if they're doing so much, hyper supreme cam, which is 1.5 degrees.
Well, it's the bright star, that's all, right? So that it's not the Rayleigh scatter you have to worry about. You just have a bright star in your field.
But yeah, it is still the case that with a 5th magnitude or 0th magnitude star in their field, they might get a little peeved. So if suddenly we have to
field, would it be exactly
true.
Field? You're looking at a different field, and if it's off by a good fraction
of
a degree, you'll never know it.
That's true.
So
it's a different geometry problem.
And
it's the opposite geometry problem.
It will be a very narrow band, so you can actually observe it in the daytime.
So, given the value, I think, of ORCAS time, we may want to think about things like potentially having it in the field of view of another instrument like Supreme Cam, but it's so much less likely than Rayleigh scatter, right?
Yeah.
No. I mean, there is an experiment where or a demonstration where people sending a laser from a spacecraft to Palomar, and it's going to be nothing other than a star. I mean, it'll be.
Right. Did you want to add something, John?
Yeah, some people have mentioned that it's actually logically possible to have adaptive optic instruments on more than one telescope on the same mountain. And so if you wanted to observe a very important target with everything you had on a particular time, you could synchronize, and the same laser could illuminate all of the telescopes on the mountain, but probably not another mountain, just all on one mountain. So it can be good or it can be bad, depending on what you want to be looking at.
Right, and I think at minimum we want to sometimes perhaps be using Keck 1 and Keck 2 looking at ORCAS.
All right, I think it's time for us to hop over to the other Zoom. Thanks everyone for the lively discussions and slides.
Thanks for participating.
See you on the flip side. Bye.